Welcome, my dear students, to Special Topics Lecture 1, which will be a systematic review of chapters 2 through 3. Before delving into the subject, I want to begin with a humorous chemistry cat of the day from quickmeme.com. This one says, how do you tell a chemist from a regular person? Well, chemists wash their hands before going to the bathroom. It's totally true. And we also wash them after. Yeah, anyway, now let's introduce you to a molecule of the day. Now, one of my students once upon a time asked the question, I'm wondering what the structures of non-monosaccharide sweeteners are. Now, he asked this in the wake of my introduction in a previous lecture to carbohydrates. So here is my answer for a few of them. These are the structures of saccharin, dulcin, acesulfame potassium, which is also known as sunnet or sweet 1. I almost said sweat 1. Sweat 1, incidentally, would probably be a worse taste. Sodium cyclamate, aspartame, also known famously as NutraSweet, and sucralose, known trademark-wise as Splenda. So there you go, any students who are curious. So here you might ask, what in the world are we doing? Well, at this point in class, we've officially covered all of the crucial chapters from our book, although we did have to skip a few that aren't absolutely necessary to the objectives of the class. But we still have about 1 month left in the semester. So what are we doing now? Well, we're now going to do a systematic review of the most critical concepts from last semester. My reason for doing this is to help you, my students, prepare for our comprehensive final exam. So in our lecture slides for Special Topics 1, which will follow in this and subsequent videos, we will gradually cover chapters 2 through 5. More specifically, after watching this series of videos, you guys should be able to determine an individual isotope's atomic weight from the weights and percent abundances of other isotopes, generate systematic names for ionic compounds, generate empirical formulas for ionic compounds, stoichiometrically balance a chemical equation, calculate a compound's molecular or formula weight, calculate the number of atoms present in a given sample, generate a compound's empirical formula from its individual atoms' percent contributions, and calculate a reaction's percent yield. It's quite a lineup, but it's all a review, believe it or not. So let's go ahead and get started, beginning with weights from percent abundances. Now, if we're given the natural percent abundances of different isotopes, as well as their individual atomic masses, we can then calculate their overall atomic weights. I'll show you how with the following problem. Naturally occurring chlorine is 75.78% chlorine-35, which has this atomic mass, and 24.22% chlorine-37, which has this atomic mass. Calculate the atomic weight of chlorine. Now, if you wish, you can compare this with question 5 from problem set 2. Now, for you, my students, I'm going to make all of these problem sets from the past semester and this semester available through Canvas. So I'm going to go ahead and show you how this is done by going to the board. When you look at the periodic table, the masses that are given for the different elements in their little respective boxes are not actually the real masses of any given atom of that element on Earth. What those masses are in the little boxes on the periodic table are weighted averages of all of the various isotopes of that element. That might sound confusing. Please let me explain. In nature, there are two different isotopes that exist of chlorine. One is chlorine-35 and one is chlorine-37. Chlorine-35 has this mass in AMU or in grams per mole. Chlorine-37 has this mass in AMU. 75.78% of all chlorines happen to be chlorine-35s, at least on Earth and maybe throughout the universe, I don't know. And 24.22% of all chlorines happen to be chlorine-37. Now, if you look up the actual atomic mass of chlorine on the periodic table, that number that you see in the box doesn't correspond to either of these. What it is a weighted percentage that combines both of these and incorporates their relative ratios. So to solve this problem, what we're going to do is this. We'll take our mass of our chlorine-35, 34.969, and we multiply it by its percent abundance divided by 100, so 0.7578. We then add to that the same thing for chlorine-37, 36.966 multiplied by 0.2422. You do that, the final number that you come up with is the weighted average atomic mass for all chlorines, both chlorine-35s and chlorine-37s. Now, I happen to have done that earlier. The number comes out to be 35.4527. If you actually look on the periodic table, this is going to be the number that you'll see in the box for the atomic mass of chlorine. Now, if we're wanting to round to the correct number of significant figures, I think that the term that we have that has the smallest number of significant figures is this one right here. It's got 4. So I'm going to want to round to 4 significant figures. So we'll go ahead and do that right here. So that would be the final answer in AMU that I would give for this problem. Got it? Good. Hopefully you can do the other following percent abundance questions on your own. That takes us to some final percent abundance questions. The first one says the average atomic weight of copper, which has 2 naturally occurring isotopes, is 63.5. One of the isotopes has an atomic weight of 62.9 and constitutes 69.1% of the copper isotopes. The other isotope has an abundance of 30.9%. The atomic weight, or AMU, of the second isotope is what? Now, I'm not going to do this one for you here, but we'll post a link here to a separate video in which I do one that's very similar, if not exactly like it. That takes us to the end of this video. Please stay tuned to the next one, in which I'll begin by teaching you how to name ionic compounds. Until then, my beloved students, have an enjoyable rest of your day.